My name is Prashant Gavari. My roll number is 20. My topic of seminar is two dimensions. Two dimensions. Exploring the flat world of mathematics. Welcome to the fascinating realm of two dimensions mathematics, where the points dance across the planes and shape reveals their secrets through elegant calculations and stunning visual patterns. What are dimensions and why do they matter? Understanding dimensions shape. Dimensions are building blocks of our mathematical universe. While we experience three dimensions daily, two dimensions form the foundation of geometric understanding. One dimension, a simple line with only length. Two dimension, a plane with length and width. Three dimensions, a space with length, width, and height. Two dimensional geometry bridges a gap between abstract mathematical concepts and practical applications in architecture, engineering, art, and computer graphics. Understanding the coordinate system, x axis. X axis is a horizontal which represent horizontal movement across the plane. Positive values move right, negative values move left from the origin 0 0. Y axis, which is vertical, which represent vertical movement across the plane. Positive values move up, negative values move down from the origin 0 0. Origin point, the central reference point where both axes intersect at coordinates 0 0. All measurements at positions are relative to this crucial point. The coordinate system invented by René Descartes revolutionized mathematics by connecting algebra with geometry in a powerful and intuitive way. Basic shapes in 2D. Triangles, the simplest polygon with three sides and angles that always sum to 80 degree 180 degree. Foundation for trigonometry and structural engineering applications. Squares and rectangles, four sided figures with parallel opposite sides. Squares have equal sides while rectangles maintain perpendicular angles with varying lengths. Circle, a perfect curve where every point maintains equal distance from the center, essential for understanding rotation, curves, and periodic functions. These function shapes form the building blocks for more complex geometric construction and real world design applications. Area calculations, formulae and application. Rectangle area, formula is equal to length into width. Perfect for calculating floor space, garden plots, and rectangular construction project. Second is triangle area. Triangle area is equal to 1 half into base into height, which is essential for roof calculations, triangular land parcels, and engineering stress analysis. Third is circle area. Area of circle is equal to pi into radius square. Crucial for circular fields, pipe cross sections, and rotational machinery design. Area calculations drive practical decisions in construction, agriculture, manufacturing, and urban planning, making these mathematical concepts invaluable in professional applications. Perimeter and its practical significance. What is perimeter? Perimeter measures the total distance around the boundary of any two dimensional shapes. It's the path you would walk if tracing the shape edge completely. Key application: fencing requirements for properties, border material for gardens, frame measurements for artwork, track distances for athletic events. Now first, rectangle. Understanding perimeter calculation ensures accurate material estimate and cost effective project planning across various industries. Now rectangle is equal to 2 in bracket L plus W. Second is circle 2 pi r, which is the perimeter, and triangle is equal to A plus B plus C, where A, B, C are sides of triangles. Now transformations in two dimensions. First is translation, moving a shape from one position to another without changing its size, orientation, and internal structure, like sliding a book across a table. Second is rotation, turning a shape around a fixed point called the center of rotation. The shape maintains its size while changing orientation through specified angles. Reflection, creating a mirror image of a shape across a line symmetry. The reflected shape appears flipped but maintains identical proportion. These transformations are fundamental to computer graphics, animations, robotics, and architectural designs, enabling precise manipulation of objects in two-dimensional space. Symmetry patterns in two-dimensional figures. First is line symmetry. Bilateral symmetry, where one half mirrors to other across a central line. Second, translational patterns. Repeated motifs that create tessellations and wallpaper like design. Third is rotational symmetry. Shapes that look identical when rotated around a central point at a specific angle. Fourth is point symmetry. Figures that remain unchanged when rotated 180 around a central point. Symmetry principles guide artistic composition, architectural design, and natural patterns recognition, revealing the mathematical beauty inherent in our world. The Cartesian plane, plotting points and graphing. Mastering coordinates plotting. The Cartesian plane transforms abstract mathematical relationships into visual representations, making complex functions comprehensible and analyzable. Key concepts: ordered pairs xy represent the precise location. Quadrants divide the plane into four sections. Function graphs reveal mathematical relationships. First, identify coordinates. Determine the x and y values for each point you wish to plot on the coordinate system. Second, locate position. Move horizontally along the x-axis, then vertically along the y-axis to find the intersection point. Connect and analyze. Join plotted points to reveal patterns, trends, and mathematical relationships between variables. The powerful tool enables data visualization, scientific analysis, and mathematical modeling across countless disciplines and applications. From 2D to 3D, extending into our world. Flat foundation. Two-dimensional shapes serves as a cross-section, blueprint, and building blocks for three-dimensional objects we encounter daily. Adding depth, extrusion, revolution, and stacking of 2D shapes create cylinders, prism, and complex three-dimensional forms in architecture and manufacturing. Real-world applications. Engineering drawings, computer modeling, and architectural plans all begin with two-dimensional representation before expanding into physical reality. The journey from two dimensions to three dimensions represent humanity progression from abstract mathematical concepts to tangible creations that shapes our built environment, technology and artistic expression. Thank you so much.